Hey guys, Pogo here, and welcome to the next programming problem of the week. This week we're going to look at making a binary decimal converter and vice versa decimal binary converter. This problem is also part of the 15 that I wrote for my programming competition, and this one actually took me a long time to do when I sat down today and tried to figure it out. A lot longer than I anticipated that it would, but it's definitely a very good problem, and you can write a nice little algorithm pretty easily. You'll notice that it says if you're in the intermediate division, you're finished. This problem was only for the advanced division. So this is one of the harder problems in the packet. So let's take a look at the problem and see what's going on. So we normally count using the decimal system, where a number goes to the next place every power of 10. So we have the ones place, tens place, hundreds place, thousands place, and that's where we go to the next digit, or the number gets one digit longer. Computers count using the binary system, where a number goes to the next place at powers of 2. So you have 1, we're all made up of, our computer binary is made up of ones and zeros. So when you get a number 2, it actually rolls over and goes up. Like if you have 9 plus 1 in decimal, it would then go to 10. The next place. If you have a 2 in binary, or 1 plus 1, it would go into the 2's place, then the 4's place, and the 8's place, and so on and so forth. So let's consider the number 163. We could fill in a table saying that there is 100. So the 100th place has 1, the 10th place has 6, there are 6 10s, and there are 3 1s. And to get back from this sort of table into decimal, you multiply each count by its place. So 3 times 1 plus 6 times 10 plus 100 times 1, and you would get 163. If we want to convert this number into binary, we fill out the table below. We start from the end, or from the largest place, which in this case is the 128th place, and then we count back to 1. And we say, okay, there's 128 in there. What do we have left? I think it's 35 left. Well, there is 064s in there. There's 132. There is 1 2 and 1 1. So again, if you want to convert back, you can simply multiply. And you can say 1 times 1 plus 1 times 2 plus 0 times 4, 0 times 8, 0 times 16, 1 times 32, 0 times 64, 1 times 128, and you will get back to 163. So since we know how this works, now that we know this information, we need to write a converter that takes a number and the type, so D for decimal or B for binary, and converts it to the other type. You may assume that all numbers are valid and that the largest number would be, that's 8 ones, or 255. And that's very important because obviously after the 128th place would be the 256th place, which means that we only need to worry about this group of places, and there are 8. The largest number would have 8 ones in it, so we'll have a maximum of 8 places for a binary number. We have our sample data here, so for example 163, and I'm saying that that's a decimal number, which means I need to convert it to binary, and it would give me 101000011. And if I did the opposite, I gave it that number and said this is a binary number, it would be able to get me back to 163. And I have here a binary to decimal and decimal to binary converter. I first of all just confirm some numbers, but we can use this to get random values to test and make sure that our algorithm actually does work. I would also recommend, I have a video that explains binary and counting with binary and all of that. So if you're confused by how binary works or anything, then I would definitely recommend checking it out. Let's take a look over in Eclipse. I have this set up a little bit. We're going to be implementing this static convert method. It will take a number and the type, and it will then convert it. So I have the Java docs written here. You get the number, there's the maximum values, the type of the number, and then the return value. And then I have this set up, so it'll print out the result of calling convert with 163 in decimal, or the result of converting that number with B for binary. So we just need to implement the convert method here that will actually convert it. So let's go ahead and get started. I'll take you through, first of all, the solution, of course, but then also kind of how I went about thinking about it and how I went about solving the problem. first thing we want to do is I created an answer variable, which will start at being 0. And in the end, we're just going to return answer. Because remember, we have this number, which is the number that we're given. And we can manipulate it, but we need to also store the answer. Because as we take chunks out of that number, we need to put them into the answer. So we need to have a second integer. And what I mean by chunks are, when you go in here and you're counting, when you count the hundreds place and you see there's 1, then you have to take that 100 out because you already used it. And then you move on to the tens place, and you have to take out that 60 there because you already used it, or else you would count it again. Not sure if that makes sense, but we will need our second variable. So first, we'll just set up our typical if statement. So if the type is D, then we need to convert to binary. If I could spell it right. Here we go. And then otherwise, we need to convert to decimal. And we're just assuming that the type will be either D or B. So let's start with binary. The first thing that I wanted to do, kind of my challenge for this, was I didn't want to use any while loops. I did end up using a for loop, and I don't know if I could have gotten around that. I'm sure that there might be some trick, but in the last video, the time formatter, I did use a while loop, and I could have done it without one, and that probably would have been a cleaner implementation. So I found a very clean implementation, very few number of lines, that does not require a while loop. But in order to do this, we are going to need to define a couple of things. I'm going to make them static and put them outside of the method. You could just put them inside of the method if you want. I want to store the binary places, and I also want to store the decimal places. And this is going to come in handy for our conversion, because we'll need to know, all of the different binary places, so that we can do multiplication later. As we take numbers, as we take the ones and zeros off of binary, we need to multiply them by their place value in order to convert them into decimal. And then the same with the decimal places. We need to use modulus to go through each number. So 1, 0, 1, 0. We need to go through each number and then convert it. So first we'll just define the binary places, and we know that these are the 1s, 2, 4, 8, 16, 32, 64, 128. These are all powers of 2. And it would go on, but I said the maximum is 255, so we only need to go up to 128. As far as decimal places, we have 1, 10, 100. And this is where I stopped initially when I was working on it, because I figured, oh, well, the decimals, the maximum is 255, so we only need to go up to the hundreds place. But we're actually going to use the decimal places in Array for a different purpose, and that's for chopping all of the numbers off, because we know that we can use division and modulus to get numbers off of the front and off of the back to multiply them. So we actually want to say we have 8, there are 8 places in the largest number, so we need to support that. So 1,000, 10,000, 100,000, million, and then 10 million. So that should be 1, 2, 3, 4, 5, 6, 7, 8. So that's good. Just so you know, underscores in numbers was added in Java 7. So if you're getting errors on that, just don't put the underscores in. So those are all of the different possible places that we could have. That's the largest. The largest number will be 8 ones, and that's 8 digits, so we'll have that covered. So first, we'll go about converting it into binary. So what we want to do is we want to step through every single binary place, starting from 128 to 1, and then given that decimal number, we need to kind of convert it. So if we're given a number like 163, as we mentioned before with this table, if we're given something like 163, we need to say, okay, there's 128, there's 128, so we put a 1 at the beginning of the number, and then we subtract 128 from 163 because we already used it up. and then we have 35 left. And we just keep going through here until we get to the ones place, and that will either be a 0 or a 1, and then we're good. So that's how this is going to work. So we're going to go through each one, and we want to start at the end, because think about it. If we have a number like 163, there's going to be either 0 or 1, 128s, but if we start with the ones place, we could say, oh, there's 163 ones in there, and that's clearly an invalid binary number. So we need to start from the largest place and go down. That's very important. So we're going to use our I counter, and we're going to do the length minus 1. We always need to do minus 1. We're starting at the end. I is greater than or equal to 0. I minus minus. So we're starting with the 128, and we're going back to the 1 inclusive. And now we have the setup. So we're going to enumerate through all of the binary places, starting from the largest, going to the smallest. And if you wanted to support more places, you could just add a 256 right in there, and then you would have more support, and you would just want to add 100 million, or just one more 0, to the end right there. And then you'd be able to support more places. That's one of the great things about this implementation, is it's really easy to scale it up. So there are two things that we're going to need to do. We're going to need to add to our answer and subtract from our number, because as we take digits off of our number, we need to put them into answer. So what we're going to do is we're going to say answer plus equals. So we're adding to answer number divided by binary places I times decimal places I. Now we need to think about what this does, because this is 1/2 of the entire thing. All we need is one more line for modifying number, which we'll do in a second. But what's going to happen here? So let's first say that we're starting at the end of binary places, which is 100. Or we're starting at the end of binary places, which is 128. And that is number 1, 2, 3, 4, 5, 6, 7, 8. And then we have here 1, 2, 3, 4, 5, 6, 7, 8. So these are both the same length, obviously, because 128th place in decimal corresponds with the 10 million place in decimal. Or 128 in binary is 10 million in decimal. So we're taking number, and we're starting with the end, so 128 and 10 million. So we're dividing number by binary places. And remember, this is integer division, and that's really important. So if we think about 163, and we're going to divide it by 128, that's going to give us 1.27, which is going to round down to 1. And then 1 times that decimal place, 1 times 10 million, is going to be 10 million. But don't think about it as 10 million. Think about it like this number up here. Because there's a 1, if you're thinking about this as if it were a decimal number, then there's a 1 in the 10 millions place, because there's a 1 followed by 7 other digits. So we're almost using the decimal places like an integer, or we're using the decimal places here, because we're either saying this result is either going to be 0 or 1. Because if the number is something like, when we have 35, when we get to the 64th place, 35 divided by 64 is a decimal, which will round down to 0. We always round down. And then when we multiply it by whatever, it's going to be 0. So the question is it going to include this 1 or is it not? So this is either going to add something or it's not going to add something. But it doesn't matter either way. So, alright, so now we're going to take a look at the number portion. And this one is going to be, it's going to look very similar, but it's a slight difference. And we're going to do number minus equals. We're going to subtract from number. It's going to be number divided by binary places I times binary places I. And I'll admit that this does look a little bit strange. It almost seems like the binary places would cancel out, and you're just saying number minus number, which is obviously strange. But we're going to actually see why. So let's take a look at this and see what's going on here. So the first part of this, the answer, is, again, so let's say we have the number 163, and we start with the 128th place. So we divide it by 128, and then we multiply it by the decimal place, which is 10 million. Well, at this point, we know that 163 divided by 128 is going to be 1 according to integer division, and we're using integer division. So it's going to be 1 times 10 million, which will be 10 million, or a 1 in the 128th place if you're thinking about it like that. So that's where this 1 will come from. But now we need to subtract from number in order to compensate. And we have to remember that answer, we're doing answer in terms of binary, and we're doing number in terms of decimal still. So we need to be careful of that. And the difference, obviously, is the decimal places versus binary places. So we'll take a look, and we'll see that, again, number divided by binary places I, so that would be 163 divided by 128, is 1.27, which would then, of course, be 1. And we can just quickly see for a second, if I multiply this by, again, binary places I is 128. So if I do this, it would normally cancel out and just be 163, which is what it looks like. But what actually happens is this part here actually evaluates to be 1. And then you get 1 times 120, which is 128. So we're subtracting it. Essentially, again, this result in both situations is either going to be a 0 or a 1. So obviously if it's a 0, then the answer doesn't change and the number doesn't change. But if it's a 1, then we add whatever the decimal place is, which would be, this number, and then we subtract whatever the binary version of that is, or the binary place, which is 128 in this case, from number. So it's just that little subtlety, but we have to remember that we're dealing with decimal and binary separately. And then again, this will either be 0 or 1 because we're doing integer division. So don't get confused by this. You'd think that this is number minus equals number, but it's not. So next we just need to do conversion into decimal. And I originally figured, it's probably going to be pretty much the same. I figured I could just swap the binaries and decimals that shows up, but it's actually a little bit different. So let's take a look at that. So we're going to be iterating through decimal places. Okay. And we're going to, again, start from the back and go down. This should be 0. Because we want to start from the greatest decimal place and then go backwards. And what we're going to do here is we're going to say answer plus equals number divided by decimal places I times binary places I. And again, this is just a complete swap of what we had up there, swapping binary with decimal. And we can quickly look, we have a binary number, like let's say we have this number, and we're going to divide it by the decimal places in index I, which is the end, which is this. Not my notes, sorry about that. We're going to divide by that. Oh, I guess that's too big of a number to give it. All right. But when we do the division, this will end up being either a 0 or a 1, and then we're going to multiply because we're converting to decimal. So again, we start with this binary place of 128. So if this is 0, answer will not change. If this is decimal, or if this is 1, rather, then we'll multiply it by the binary place, like 128. And we're just adding that to answer. So we're basically going through each number, and we're starting with this first number, and we're saying, oh, this is a 1, and it's in the 128th place. So we're adding 128 to answer. Then we go to the next number right here, and we say, oh, this is a 0, so we don't do anything. And then we see a 1, and we say, oh, here's a 1. This is in the 32nd place right there, so we just add a 32. And that's essentially what we're doing. But of course, we need to change number again, because every time we use something, every time we take one of these 1s and we use it, we need to get rid of it so that it's not there anymore. So in this case, we're actually going to do number mod equals decimal places I. So we're not doing the same division. I'm not 100% sure if the division would do the same thing, but I think that this just makes a little bit more sense. So if we start the number off at something like 101000011, and then we get to the 10 million right here, when you do the modulus with this, these are both 8-digit numbers, it's just going to chop off the first number, and then we'll be left with 0, 1, 0, 0, 0, 1, 1, and then that 0 in the front will go away. And that's one important thing. Since this returns an integer, it will omit all of the leading zeros. So if some number has a 0 in the 128th place, it just won't show up because we're dealing with integers. You could modify this to work like a string, and then you would essentially just concatenate ones and zeros, or just do some kind of a conversion at the end. You could still have answer as an int, but then convert it to a string and put zeros in front as needed. So if I run this again, you'll see that 163 in decimal then converts to the number 101,00011, and that's what we wanted. And when we convert that exact number into binary, or when we convert that number, which is binary, then we will receive out 163. So let's just try this out with a couple of different numbers to ensure that it works. So we'll first test it with our maximum, which is 255, or that's going to be, all of these would be 1s. Let me just make sure that's 8. And then if I run this, you'll see that 255 into decimal gives us 8 1s, and 8 1s as binary, rather, as decimal. 8 1s as binary gives us 255. So one last, we'll just quickly try a decimal of 29, and then it gives us this binary value. So we can try that for a second. So if I want to convert 29, which is a decimal, it should give me out that number, obviously without the zeros in front, 11101. So it does do that. It omits these zeros in the front because it's an integer, it's truncated, but it does still work. And obviously if I take this the other way, and I say that that's binary, then it gives me back 73. Okay, so there was the issue. The issue, again, with the way that integers work, if I stick these zeros in the front, it will still confuse it. Actually, I believe that when you stick 2 zeros in front of a number, it becomes an octal. So I think that that's actually what's throwing it off, unless I'm wrong. I could be wrong. But these zeros in the front are just throwing it off. So you want to make sure that you don't have any leading zeros. Otherwise, you would just want to modify the code to handle for it. But assuming that we have numbers that are valid, then it will work. And I think that that's good enough for the challenge that I wanted. Because, I would implement it like this, and then I would just have the processor or the submission program check based on these numbers, and I would be happy with this. So this is this is a pretty good decimal to binary and binary to decimal converter. Took a little while to make, but it's good when you kind of think of a puzzle like this and you solve it out in code. And then you kind of have this little algorithm of converting between binary and decimal, and then not getting confused between places and whatever. And this is also nice because you can just stick new numbers like 256 and 100 million at the end, and then you would have better support for more numbers. So as always, subscribe if you want to see more, comment with what you want to learn. If you like this video, click the like button, and I'll see you guys soon with some more programming. Bye for now.